Okay. So, welcome. Thank you for having me as a speaker, Matt and Dan. Although it all kind of cropped up from how me and Dan recorded a podcast, and then he was like, "Hey, do you want to come do a talk? Let me speak to Matt as well." And they both agreed, and here I am. So I will be talking about gRPC. We will cover the basics and a bit more in gRPC today. A little bit about myself. I am Poornima Nayar. I'm a freelance .NET developer. I'm also part of the Women of .NET initiative, who helps mentor and be friends with any woman in tech or anyone who identifies as a woman in tech. I live in Berkshire, UK. I'm a Microsoft MVP for developer technologies, and I'm also an Umbraco MVP. For those who don't know what Umbraco is a .NET-based open source CMS, and my day-to-day work is heavily around Umbraco and building web applications with Umbraco. And I just love the process of content creation, which is why you would find me doing a lot of these talks. Non-work me, I'm a mother. I have an 8-year-old daughter who I spend a lot of time with. I spend a lot of time reading, and I'm also a student of Carnatic music vocals, Carnatic music being a stream of Indian classical music. And that's my Twitter handle, should you wish to connect with me. I don't know for how long or whether I'll move to Mastodon yet, but there we go. There I am. I'm on Twitter. Talking about gRPC, it's a modern open source high performance remote procedure call framework. So it's a flavor of a remote procedure call. And the remote procedure call, as per Wikipedia, the definition goes like this. A remote procedure call is when a computer program causes a procedure to execute in another address space, commonly another computer, which is coded as if it were a normal procedure call without the programmer explicitly coding the details for the remote interaction. Very, very long definition, but I had to do this. But what it means is I have a computer program and I invoke a method, and it is invoked as if it was a local function call. But in reality, when that function call executes, it jumps the network and executes elsewhere. So a local function call, a remote function call programmed as if it was a local call is what remote procedure call is all about. So there's that location transparency, or it's point-to-point communication. That is what remote procedure call gives you. Talking about the program or the workflow in a remote procedure call, we have the client and the server. My client functions call what is called a client stub. A stub is a representative of the function that I'm trying to invoke in my program. So it is a representation of the actual server function. So the client stub is also responsible for packing the parameters that I give it using a process called marshalling. It then invokes the runtime on the client, which then goes and invokes the runtime on the server, and then invokes the server stub, which through a process called unmarshalling unpacks the parameters and then calls the actual server functions, which executes, and I get the response all the way back to my client. This is RPC in a nutshell, and gRPC is a flavor of RPC. There are many, many implementations of RPCs across various different programming languages. RPC is not something new either. RPC goes back to 1970s and 1980s, but gRPC is a flavor of RPC. And what Microsoft has done is it's brought down gRPC to the .NET realm. So they have written like a library for gRPC in .NET with all the compiler support. So gRPC is Google's implementation of RPC, and it was called Project Stubby, and it was made open source and called gRPC in March 2015. And from .NET Core 3.0 onwards, we have official support for gRPC in the .NET realm. And a word about it, because WCF was the preferred or the framework that we had in the past for remote procedure call. WCF remains .NET Framework only, or there is minimal support for WCF in the .NET Core world. There's also Core WCF, which is a community project. But if you are looking at a properly, officially supported framework for RPC requirements in your business, gRPC is the favored or the recommended platform these days, or the framework these days. gRPC favors contract-based API development. So you have a contract that you write and you try and implement or fulfill that contract. And gRPC is designed for HTTP2 and even beyond, because Microsoft or the .NET implementation of gRPC is the first one to go back with the proposal of how it should work together with HTTP3 features. So the first technical term which we need to introduce ourselves with gRPC is protocol buffers, which is the interface definition language as well as the message exchange format. So the contract that I write out, that language is protocol buffers. Also the messages that goes between the client and the server, that is also protocol buffers. And protocol buffers are Google's open source mechanism to serialize structured data. Google Cloud uses protocol buffers. If you have been dealing with Google Home devices, so you'll come across protocol buffers, but there is no reason why you cannot use protocol buffers in your normal web APIs as well, because it's a way to serialize your data. So you can actually bring down protocol buffers as a serialization and deserialization format into your web APIs as well. But protocol buffers are language neutral, it's platform neutral and extensible, and it's incredibly smart in the sense that it is forward as well as backward compatible, which means with a bit of love and care, you have versioning sorted out for you by default. It doesn't take as much effort to version up a gRPC API as compared to a RESTful or HTTP API. Talking about the requests and responses between the client and the server, they are called messages in the gRPC world. And each message is a record of key value pairs called fields. So a message looks something like this. So it has the keyword message followed by the name of the message, and then you have the field. Each field has a data type, a name, and a number attached to it. These messages, for transmitting purposes, they are transmitted in binary format, so that keeps their sizes quite low. And unlike JSON, which uses the name of the field as the identifier while serializing and deserializing the data, with protocol buffer messages, it is done against this unique number. So this unique number is of great importance. So when it is transmitted, the value of the first name field is against the number 1 rather than the name of the field itself. So that's another reason why protocol buffers are smaller in size and the messages are smaller in size, and that gives the performance boost as well that we get from gRPC. And the next technical term is proto files, which these are files with .proto extension, and these define the contract of the API. So we have the contract of the API, we have the service definition in a proto file as well. So typically you would have one service in a single proto file, but each of those services can have as many methods as you need. And the proto file also can contain the messages that are sent between the client and the server. So this is the proto file that I took from Visual Studio's out-of-the-box template. We'll go through the syntax very briefly. The syntax of the proto file starts with the syntax definition, which is proto 3 at the moment. Then we have the C# namespace. So with proto file and gRPC, there's tooling that kicks in and generates some code for you. So we'll talk about that in more detail shortly, but that code, when it generates, you can specify a namespace for your C# code, and that is what this option lets you specify. Then you have the package keyword, which is the namespace for the protocol buffer itself. This is of great importance, which I will tell you why later in the talk, but in order to prevent namespace clashes for protocol buffers itself, we can specify namespaces for protocol buffers, and that is what the package keyword helps you do. Then you have your service, which is greeter in this case, and your RPC definitions. So each method in a service is called an RPC or a procedure. So every RPC starts with the keyword RPC. Then you have your request and response messages as well. There are ways to move these request and response messages away from your proto file and import them, just like you would import your namespaces in C#. That is also possible, but let's keep it simple for now. Let us have the messages in the proto file. And what happens behind the scene is when MS build job kicks in, or when you Visual Studio builds in simple terms, the service that you have in your proto file gives rise to an abstract base class. So it has got a certain naming convention in the form of service name dot service name followed by the keyword base, and it is an abstract class. And each of the RPCs becomes virtual methods in that abstract class. And the request and response messages gives rise to plain POCOs. So the data types are inferred for you, and the code that gets generated also follows the naming conventions, the best practices for that particular language. So in this case, the C# code that gets generated conforms to the Microsoft specified standards and conventions and practices. That's on the server side. So there's equal code generation on the client side as well. So for a client to communicate with a gRPC service, you need a generated client, and the tooling helps you generate the client as well. And in this case, every service that I have gives rise to a client with the naming convention service name dot service name followed by the word client. And there are stubs created for every RPC in my service as well. And we have POCOs generated for the request and response messages. And this code generation is controlled by a tag in the CS-proj, which is the protobuf tag. And once you have the protobuf tag, it indicates that I should treat the file as a protobuf file, and it should kick in some code generation depending upon the gRPC services attribute that you have in here. So if it is set to server that I have shown here, it generates just the server-side code, but it can be set to both, in which case both server-side as well as client-side code just gets generated, and that's the default. If you leave out this gRPC services attribute, both client and server-side code gets generated as well. You can set it to server. You can set it to client as well, in which case just the client-side code gets generated. Or if you set it to none, no code gets generated. For example, as I have said here, you need to have this proto file so that you can generate your client and server-side code. But you might want to have the proto file available to your external clients as well. You might be having a public gRPC API, and you need this proto file to actually generate your client-side code as well, in which case you need to make your proto file kind of distributable as well. So if you have only .NET clients consuming it, you might actually release it as a NuGet package, in which case your project would have like a collection of proto files, and you just serve up the NuGet packages as files, and you don't have the code being generated at all. So there's a reason why we have the none as well. Talking about some of the tooling that is available to us, we of course have the project template in Visual Studio. What we would find in that project template is this NuGet package, gRPC ASP.NET Core, which is like a meta package, which has the server, the client libraries, when I mean server, the server library, the client library, and all the tooling that is needed as well. If you are just after the server-side library, you can use this package, which is gRPC ASP.NET Core Server. There is gRPC Net Client, Google Protobuf, and gRPC tools, which are needed for the client aspect. So gRPC Net Client is the client library. Google.protobuf is used for serialization and deserialization. And gRPC.tools is what contains the magic for code generation. The gRPC.tools is baked into the ASP.NET Core server, so you wouldn't have to worry about it, but gRPC.tools is needed on the client to actually build up that client code. And inside gRPC tool is what is called a PROTOC compiler. And that PROTOC compiler understands C#, which is the reason why we have C# code in place. So PROTOC compiler alongside a special plugin helps you generate that code for you. And PROTOC has support for all these languages and many, many more. So which means that gRPC is a very good candidate if you have polyglot systems, or if you have your API that is that needs to be consumed by clients of various different languages. What you have to do is that make your proto file distributable as an artifact to your clients out there, be it C#, be it C++ or Node, and they would be able to get hold of your proto file, use the PROTOC compiler, and generate the client-side code and start connecting to your server and use it. So that is how gRPC works in a nutshell. So let's go and see some code in action. So in my project here, I've got some setup done. So we'll speak about the basic setup first. I've got a very simple server application running, which is nothing else but the Visual Studio out-of-the-box template itself. So as you can see, I have a proto file, which is included as the proto buff. And I've got the package reference, which ships with which is included as a part of the project template itself. And I have my greet.proto here. And this is exactly what you saw in my slide as well. So when I build this project, what happens behind the scene is that it goes and generates the code for me, and that code can be found in the debug folder, in the protos folder. So for every proto file that I have, there is 2 different C# classes that gets written out. One is the greet.cs, which contains the POCOs. This is just the POCOs. And the greet.grpc.cs actually contains the base class. So if I go and search for greet base, it should be there. So that is my service, the class which gets generated from my service. And that is my virtual RPC method. So in its native form, if I start using this RPC method without giving it an implementation, what I would get is an unimplemented status code or an unimplemented exception. So we need to give this our own implementation, and that can be done by using my greeter service, which inherits from the base class that we just saw. And I can override my RPC method to give it my own implementation. So the RPC method would take the request message as one of the parameters. And all RPC method also gets the server call context, which gives me information like the host, the domain, where the call came from, any information that is relevant to the call comes in the server call context object. So if you have authentication, the claims principal, all that authentication details also comes in the server call context object. So it's an incredibly useful object. Say, for example, in my override, I am writing out the context peer and the context host. So all that information is available from the server call context for me. Talking about the client, as I said, we need a strongly typed client or a generated client to communicate with this service. So I've got a console application here called gRPC basic client. And I've got this greet proto added into my client as well, because I need to generate that code for me. So for this, what I have done is if I go into add service reference, it gives me option to add a gRPC service. So it looks quite similar to how we used to add a web service in the WCF world. So that's a kind of same pattern. And in my CS Proj, as you can see, it is set to gRPC services client. So this is another way of specifying that attribute, and it generates only the client side code for me here. And in my program.cs, I can use a gRPC channel to connect to my local host. So gRPC channel is like a connection to the remote server. It's a very heavy object, and it's one of those objects which needs to be cached and reused if you want to conserve or if you want to gain some performance, because it involves multiple round trips to the server to actually create that gRPC channel and establish that connection. So be very wary of how you use your gRPC channel. Your gRPC channel can actually be a connection to the server, but you can actually use multiple clients on it. So if you have a greeter client, then you have a to-do client, all those clients can make use of the same channel. So reusing that channel is very important. But I have only one gRPC client here, which is the greeter client. So once I create my channel, I can use that channel to create my client and invoke that method in my proto file, which is the say hello method, using the client stub, which is being created for me. And then I can use the hello request object to send that to the server. So this is a gRPC in a very basic gRPC app. So let's get this running. So let me first start my server that is there. And then .NET run again on the client. So it is actually sending the name client to the server. And on the client side, it has processed that information. It's just sending back that information and says hello, hello to the client from the server. What it is actually doing behind the scene is it's actually doing an HTTP2 post to the server, and it works out a URL to the server because it's essentially a middleware that does that. So that is gRPC in its basic form. Moving on, when we talk about gRPC, we need to discuss the gRPC modes because gRPC works very well with HTTP2 and it's been designed for HTTP2. So it takes advantage of all the nice features of HTTP2 like request multiplexing and streaming capabilities. So what we just saw was unary, where you have a client and a server. The client sends a request message to the server and the server sends back a response message. A single message in, single message out, that is unary. And the definition looks like this: RPC, the name of the method, followed by a single request message and a single reply message. So that's one of the key things with RPC. You always have a single request message and a single reply message. You cannot have multiple inputs and multiple outputs. That message object can contain as many fields as you want. That is not a problem, but it has to be a single kind of object in its entirety. And we saw the implementation, which has the request message and the server call context, and you can then give it whatever implementation that you need. And we saw this kind of call, which is the synchronous blocking call, which is what I showed you. But unary also gives you a asynchronous non-blocking call as well, which you can use. Say, for example, if you want to make use of the response headers that comes back from the server, then you need to make sure that you use the asynchronous blocking call, because the unary method, the blocking call that you have here, gives you a reply message, while as the unary async call gives you the async version gives you an async unary call object, which contains both the reply message as well as the metadata. So that is a special thing there. So you have two versions of your same method there. The next one is server streaming, in which the client sends a single request message to the server. That acts as a trigger to the server, which opens up a stream, which sends data back to the client. So in the stream, there is multiple message being sent out in the same request. So streaming is like a long-standing connection between the server and the client, and you can have multiple messages going through the same request as well. So that's taking advantage of the HTTP2 feature. And the definition, the syntax of the method definition looks like this. RPC, the name of the method call doesn't change. You can give it any name that you want. It is a single request message again, but what you get back is a stream of messages from the server. So that is one key difference here. There's the stream keyword. And one thing to notice here is that once the client opens up or sends that request message, the client cannot then send in further messages. So often the streaming methods are long-standing connection between the client and the server. So if you want to cancel what is happening on the server or the processing on the server, you need to send in a cancellation token or specify a deadline. With cancellation token, it is the client taking control, saying that I want to cancel this, so cancel this. Or you can set a deadline, which is like, I will wait for this amount of time for the process to finish. If it doesn't finish by then, just kill that process that is running on the server. But no matter what you do, what you need to make sure on the server is that once the gRPC call has ended, that cancellation token or the deadline is given into your further processing operations like the database calls or anything to stop that from processing as well. So there is that fact that you need to factor in as well. So if you want to see how you can connect to a server and start a server streaming, so we start off by creating a channel and a client, and using the client, you start the server stream demo method by sending in a method, and then you wait for the stream and the messages from the server, and you can keep on reading from that. And in this instance, the client will keep on reading until and until there is no more messages to be read from the server. The minute the server opens up a stream and a message is placed into the stream, that becomes available to the client straight away. And on the server side, to see how the method override works, so you have the method which I have overridden. There is a request message. There's also a stream writer for the response stream that goes back to the client. And of course, you have the server call context object. In this case, I'm just looping through 1 to 10 and sending back a hello. And that is all what is happening. And as soon as I have the write async placing the message to the response stream, it becomes available to my client. The next one is client streaming, in which the client sends in a series of messages to the server. Again, there's a long-standing operation with multiple little messages going through to the server. Once all the messages has been received, the server gets notified that the client has stopped streaming. And at that point, the server can process the data and then return that result back to the client. This is one area where you can get a performance boost, especially if you have a large file to be uploaded. You can break it into chunks and then use client streaming to upload that file to the server. In this instance, you would have a single reply message, but you would have the stream keyword in front of the request message. That is the key difference in the method definition here. Everything else remains the same. And talking about the client call, again, setting up the gRPC channel and the client, I start an instance of the async client streaming call, and then I can place any messages into the request stream here. And once I have called the complete async method in the request stream, that is a notification sent to the server that, hey, the client has stopped streaming. And once that is done, the server starts processing, and then I can await the call on my client to get back any messages from the server. And on the server side, the override looks like this. There is a request stream that comes in and a server call context again. I can read through to the end of the stream using the move next method. I think there is also another method which I can use for reading from the stream, but you can use either of that. And I send back a single reply message back from the server. And the final mode is a mixture of the two streaming modes, which is the client and the server streaming mode, which is the bidirectional streaming, in which the client sends in a series of request message and the server streams back as well in response. So which means in front of the request as well as the reply messages, you would have the stream keyword. So it is instances of request message that are sent in and instances of reply messages that comes back. So talking about how the client, the bidirectional streaming work, I set up the call first to the bidirectional stream demo, and that is my method there. And I start listening from the server, and then I start placing messages into my request stream. At one point, I tell the server that the stream is complete, and then I await the task from the server, which I'm listening to. And on the server side, I have both a request stream as well as a response stream and the server call context object. So I can read from the stream, and for every message that I read from the stream, I can send a message back, or I can have reading and writing happening at the same time, or it can be independent ones. So there is all sort of complex scenarios possible with this. So let us see if I can get a demo working here again. It's the same code that I am using in my GitHub sample repo. So let us see one of the client in action. Sorry, CD gRPC service. Oh.
So that's gRPC service. So this is my service, which contains all the code that I've been showing you through my slides. So let's do a .NET run and get my service up and running. Let's kill the client and go back up. I think I'll just show you the bidirectional streaming demo. So that is it, .NET run. So it should send a hello from the client. The server receives it. And for each of the message that is read from the client, it's sending a message back to the client, which I have received here as well. You actually need a delay in between to see the messages flowing in, but I've just worked it out this way. But again, it is actually doing an HTTP post to a URL, which it works out. So I'll share the GitHub repo with you at the end of the talk so that you can actually run this yourself as well. We can also send metadata with gRPC services. There's request headers, which you can send in from the client. There's also response headers, which you can get back from the server. There's also response trailers in addition to response headers. So there's a difference between the response headers and trailers in the fact that response headers are sent alongside the response. So as soon as the first response is sent out, say in case of streaming method as well, the response headers comes through, but response trailers are given once the response is complete or once the server has finished all the processing. So this is particularly helpful when you have streaming going on, especially with the server side or the bidirectional streaming, where if you have an instance where X number of messages are only processed, the rest failed. So you can actually send in an RPC exception back with all of the details why it failed in the response trailer. So that is the use of response trailers. Response headers actually are more generic information. It contains more generic information about the call itself, while response trailers are particularly information that pertains to the response or the call itself. So it's more focused on the response itself, the data that usually comes back in the response. And how would you access or you make use of these headers? So this is on the server side. So if you want to access the request headers, that is available in the server call context. So context.request headers gives me access to the request headers. And if I want to add response headers, I can do that as well. So the headers, be it headers or trailers, it is done or it is created and added as metadata object, which is like a collection of key value pairs. So I have a new metadata object with a key value pair here, which I can add to the response headers. If I want to add a trailer, I can do the same thing as well, like so. And I can send back the reply message. So once I send back the reply message on the client, I can await that asynchronous non-blocking call to get access to the headers and trailers. And on the client side, if I want to send in a request header, I again make use of the metadata object and create that key value pair dictionary and send that metadata alongside my async unary call. But I can do that in my in any of the gRPC modes as well. I have chosen the unary call here, and if I want to await or receive the response headers on my end, particularly in the case of unary call, I need to make use of that async async non-blocking call, which is what I've done here. And I can use the get trailers method to get the trailers as well. Get trailers is available only after awaiting the response as well. So there's that thing that you need to think about as well. Now, talking about gRPC, this is at the end of the day an API. There is a need for versioning here, be it any type of API. But in this particular instance, what is more important is that we have that contract of the API, which is the .proto file, which is kind of shared between the client and the server in some manner. So if I have a public service, I will have the proto file on the server side. I might be making that proto file available to all my clients who wants to consume it, so that they can then generate the client and use it. So that proto file gets kind of shared to all the clients out there. I might want to update my proto file. The clients might be updating the proto file themselves as well. So there is that which cannot be kind of overlooked. But no matter what we do, we need to make sure that all the existing clients are happy and all the future clients are happy and everything continues the way it is and nothing breaks. So that is the need for versioning. And good news is that gRPC thinks of versioning right from the word go. So if you are aware of what you need to look for, you have a fully versionable and maintainable API right from the word go. So there are certain things which might be useful here. What are the breaking and non-breaking changes? So usually an addition, adding a new field or a method or a service is a non-breaking change, because with protocol buffer messages, there is no concept of nullability. If a request message, something is added to the request message during deserialization, the default value for that particular data type is assigned to that field. So if you have an int field which is added to the request message, it is set to 0 when you deserialize. Similarly, if something is added to the response message, again, it is set to unknown fields default value and then discarded. So adding a new field to a message or a new method or a new service is a non-breaking change. That is fine. But when it comes to removing fields, the things can be quite different. If you remove a field as it gets deserialized with the default value, shouldn't be a problem. But then you can have behavioral changes in that application that consumes that API, because when you have, say, an int field removed, an int field is set to 0, which is the default, the actual value of 0 and the default 0 might be different as far as your application is concerned. Similarly, a Boolean value of false versus the default Boolean value of false might be different in meaning when it comes to your application. So removing fields can be a tricky one. It could actually change the meaning of what gets served to the client. So be very careful of how you do that. But the way you can overcome it is by using the reserved keyword to prevent future addition of the same sequence number or field name. So if you remove a field name, make sure that nobody in the future comes and adds it again. And that can be done by using the reserved keyword. You can set a number to the reserved, a series of numbers, like a sequence of numbers, or even a field named reserved. So in this case, the number 2 is reserved, in which case no one can come at a later date and add a field at number 2, and so on. So this is one way to make sure that, you know, nothing gets added by default or by accident. When it comes to modifying fields, there are certain data types which are compatible, but just because you have those compatible data types doesn't mean you need to use them, because changing of data types of field could result in loss of data. Changing the name of fields or messages can change the verbal meaning that I explained before. And finally, field numbers. If you are thinking of changing field numbers, do not change it, because that can be a breaking change. That takes us to what the breaking changes in gRPC are. Changing the field data type could be a breaking change at some point. This can break the clients out there. Changing the field number can be a breaking change. It can break the field clients out there. Renaming a package, a service, or a method can be a breaking change. Removing a service or a method is again a breaking change. So that brings us to the package keyword and why it is important. So if I look at this path that it has worked out here, there we go. So this is using this gRPC service that I have here called the bi-directional. So let me just work it out. So the proto files are here. Okay, so I have this proto file here called the demo service, which is what my service is using. And I have my method here, which is the bidirectional stream demo. And I have my C# namespace and the package called gRPC demo. When the bidirectional stream demo method is invoked by a client, what it does, or the path it works out, is the base URL slash gRPC demo service. The gRPC part that you see here comes in from the package name here, and the demo service that you see here is the name of the service. And that slash, the name of the RPC method, is the path that it works out. So the path that works out is the base URL slash the package name dot the service name slash the RPC method name that you're trying to invoke. This is the reason why removing a package name, or removing a package or renaming a package, renaming or removing a service, or renaming or removing a method can be a breaking change, because the path to the server completely breaks for the client. That is why it is a breaking change. So, but then think of this example. We have this package name that you find here being a part of your URL itself. So suppose I name this package as something like gRPC demo.v1, the URL that it works out to this particular service would also change. In this instance, it would be gRPC demo.v1.the demo service slash the method name. So if I want to version my services, the key here is the package. So I can actually provide a .v1 or .v2 instance as the package name to the same proto file and keep on extending it. And in that way, I can have the versioning done and also make sure that my existing client are happy, and the future client, which gets a new version of the service, continues to work against that new version. And the old clients doesn't even know of the new version, whereas the new clients doesn't even know of the old version. So existing clients are happy, the new clients are happy as well. So let's see how that's been worked out in my code for you. So let me bring up that gRPC versioning. There we go. So I have two versions of my service. So I have a v1 greet.proto, which I begin with, and suppose, say, down the lane, I want to add new methods or change something. So what I would do is, whenever you start a gRPC service, I would add a .v1 or some sort of indicator to make sure that this is the v1 service or the v1 version of my service. So that is my native, like out of the box Visual Studio Proto that it has been given. All I've done is added a .v1 to it. And if I want to keep updating and come up with a new version, what I would do is I would go and create a new proto file, but give it the name .v2 at the end of the package name. And what it does behind the scenes is when the code gets generated, the code also is slightly different. If I look at the debug, again, for each of the proto file, there is two versions generated. So in my greet.cs, the namespace is greet.v1. So what happens is that if I don't have the option C# namespace specified, it goes and picks up the package name itself as the namespace of the C# code that gets emitted out. And that's what has happened here. The namespace is the package name. And for my v2 code, it'll be the v2 namespace that it picks up. But the real show lies in the fact that I can have two different clients, and each of them talks to specific APIs, or the v1 or the v2 API. For example, in my versioning.v1 client, I talk to only the v1 part of the service, or the version 1 service, because the greet.proto that I have here is the v1 greet.proto. And in my v2 client, the proto that I have is the greet v2.proto. And because I have only one version of that proto file, the code that gets generated corresponds to that particular proto file. So if I run my service, so let's run the service and see and show you what I mean here. If I can kill it, that is cd gRPC versioning.net run. So that's my service up and running. If I bring up my client and come on. Okay, cd versioning v1.net run. So this is my client, which has got the version 1 proto. And when it communicates the server, what it uses is the v1 proto, which means I will be only communicating the v1 part of it. And the code that gets generated in the client is only the v1 because I'm only using the v1 proto. So suppose that this is our existing client, the client which started using your API when it was at its version 1. I haven't done anything. I have changed the server already to have a v2, but my client doesn't know anything about that v2 server, but the client is happy and communicating to the server. And now if I start running the v2 client, set debug, start a new instance, what happens here is it should go and talk to the v2 instance. And what happens here is it talks to the greet.v2 proto. So this is my new client, which has come on board. It gets the v2 version, or it has upgraded to the v2 version. It is talking only to the v2 version of the API. It doesn't concern itself with the v1 version of the API at all. So the package keyword is the key to your versioning of the API here. So that is the API versioning covered. Talking about gRPC hosting, you can host it on Azure Kubernetes Service, container apps, Azure App Service. Linux plans are supported. If you want to use Windows plans, then you can only have gRPC Web, which is a way of using gRPC on the browser if you want to bring gRPC down to the browsers, but it doesn't have the client streaming or the bidirectional capabilities. So you can have your gRPC services hosted on Windows Server 2022 as well. But if you want to track the progress of where Azure is with gRPC, this is a good GitHub repo, GitHub issue to track it on. One of the last topics of the day is gRPC JSON transcoding, which I wanted to cover, which is an extension to ASP.NET Core, and it's a feature for mapping between a gRPC method and HTTP endpoints. In single words, you can build a single API service and host something as a single API, but that API contains both gRPC and an equivalent HTTP API. So if you have an existing gRPC service, but you want to extend it to have an HTTP-based endpoint as well, like an HTTP API, gRPC JSON transcoding can come to your help. So one of the key benefits of this is that with gRPC clients, you need to have that generated client, but with introducing the JSON transcoding, you can lower that barrier to the entry, which means any client which can issue an HTTP request can use your gRPC endpoint. What happens is you have a REST-based client or any client which can issue an HTTP request. It talks to the gRPC service using HTTP 1.1 as well as HTTP 2. Sorry, that's a mistake in my slides here. And it communicates using JSON rather than protobufs. And it uses your well-known HTTP methods and verbs like get, post, put, patch, delete, all of that. And it uses system text JSON as the library to serialize and deserialize on the server. And the server sends back a response in the form of JSON. And that's not all with .NET version ASP.NET Core 7 and .NET 7. We have experimental open API support for this part of the gRPC service as well. So you are effectively extending your gRPC API to be an HTTP endpoint as well. And what helps you do this is what is called HTTP rule, which defines the schema of gRPC to REST mapping. And these are done as annotations on your gRPC methods. And each HTTP rule specify a URL path template and an HTTP method. What we are sending to the service is JSON or request body or query string parameters or route parameters that then gets mapped internally to the protobuf request message. So I send in some data, the protobuf message is formed internally, and then gRPC is invoked internally. And then what happens is that once the output protobuf is formed, the message is formed, it then gets converted to JSON, and that comes back to my client. So how the route parameters or query strings, or say the request body gets mapped and the request message is formed out of it, and how the protobuf message, the output, maps to the response body, that also becomes a part of the HTTP rule that we specify. So if I show you a quick example, so I have this project here. What you need to get started is the usual ASP.NET Core gRPC packages, but on top of that, you can add this NuGet package called gRPC JSON transcoding. And I need to have my services registered like so, add JSON transcoding. And yeah, that is all what I need. And once I have that, say I already have a grid.proto or some kind of gRPC service already up and running. What I can do is I can have this proto file called Google API Annotations Proto, which needs to be in my solution, which is here, the annotations proto. And I also need the HTTP proto in the same folder. I can import the annotations proto, which means like it's equivalent to bringing in a namespace. And I can start annotating my RPC methods. So this is an example annotation where I'm saying, hey, for this gRPC method, I want it to be available at this URL and should be invoked using an HTTP GET. If I want to specify route parameters, I can do that. So in this case, I'm specifying an ID route parameter. And when it tries to form the to-do item request, the to-do item request is here. The ID, the route parameter that comes in, that value gets matched to the field of the same name. So the ID route parameter matches to the ID field in my request message. So that is another way of doing or matching up the values. If I want to do a post or a put, what I can do is I can actually have the request body that comes in mapping to the request message itself. So in this case, I'm using the post annotation. And I'm saying that with the star message, whatever comes in the request body, map it to my message. So it'll do a comparison of what comes in the request body. And for every field that it finds in the JSON, it goes and matches itself to the field of the same name in my request message. And not only this, I have Swagger support as well for this. The Swagger support or the OpenAPI support is experimental at this point of time, but I can have Swagger and I can test my APIs like you would do with any HTTP API. There we go. So that is OpenAPI support. That is done using this experimental package, gRPC Swagger, and I also need a bit of work like you do with your native OpenAPI, that is enabling gRPC Swagger, the services, and also having the middleware setup. So that is all about gRPC JSON transcoding. Some of the advantages and disadvantages. With advantages, we have lightweight messages, high performance, the built-in code generation that we get, the streaming options, the reduced network usage with protocol buffers because they are smaller in size, and of course, gRPC services are scalable. But this is a contract-based API, so there is a coupling between the client and the server. There's limited browser support. So if you want to use gRPC on browser, you need to resort to gRPC web or gRPC JSON transcoding, which gives you both unary as well as the server side streaming, but not the client or the bidirectional streaming. gRPC is for point-to-point communication. So if you want to make use of all the gRPC features, you can have communication between microservices, IoT devices, all communicating to your gRPC service. Anywhere you want to bring in a browser or a browser-based application, gRPC is not very well suited for it. The reason being it relies on HTTP2. Now, the detail I could find out is that the control that is needed to send out a web request using a gRPC client on the browser, that level of control cannot be provided by the browsers. So this is what I could gather from MS Docs, but I have been trying to read up more and figure out what more can I find out just to kind of satisfy my intrigue, because I am just tired of saying it doesn't work on the browser. There is zero discoverability. You need to make sure that your proto files are documented in some way or the other so that you can give it to your client. And of course, protocol buffers, the messages are communicated in binary format, which makes it difficult for debugging. Because it's not meant for humans to read, it's meant for computers to read, because it's point-to-point communication. If you want to test your gRPC service, you can use gRPC curl, which is a command line based tool. You can also use gRPC UI, which is a nice UI based on gRPC curl. There's Bloom RPC and Postman as well. Some of the use cases: microservices, IoT device, polyglot environments, and whenever you have streaming requirements, gRPC can be a great candidate. And that's an overview of gRPC, some of the things in gRPC, and that is a link to my resources. So I hope you have learned something new today, and that's it from me.